the main aim of this talk is the following. So, as you can see, the title is Introducing the Expanding Universe Without Using the Metric. The background is fairly straightforward. You all know that in order to really teach general relativity, you need an awful lot of formalism. Such a lot of formalism, in fact, that even the usual mathematical training of physicists does not cover all of what you need. So usually general relativity courses teach their own mathematics because it is not part of the standard mathematics curriculum. In the context of this conference, where we are all aiming to take modern research, in this case modern cosmological research, and take this and bring it to students, to high school students, even to undergraduate students, that is a huge obstacle, this formalism. So a lot of people have thought about this, and there's certain ways that you can circumvent the formalism. There's various things that will help you, various principles that you probably know, the equivalence principle, the Newtonian limit, and of course the symmetries that are associated with the simplest solutions, the simplest scenarios within general relativity that we're dealing with. But it's still an interesting question, and I believe we are still making progress on this question: how far can you get without the formalism? So in the spirit of this particular conference, where it's all about the darker side of cosmology, the question is, how much cosmology can you do without the formalism? And the ambitious goal is, can we understand this, really understand where this comes from, which relations you need to use? This diagram that has the redshift, that has the distance module, which is something like a relation between the brightnesses of objects, how dim do they seem, how far are they away? Can we really understand this without looking at the metric, without looking at tensors? And I believe we can. All right, so this is the general outline. We're going to talk a little bit about about what cosmology does. We're going to look at a simplified version of general relativity. We are then going to look at the usual simplified models, what you know as the Freedman, Lemaitre, Robertson, Walker, FLRW models. Then, after we've defined these models, we will have a look at what scale factor expansion, this cosmic expansion, actually does, what consequences we can derive. Then there's a question of dynamics, what determines how the universe is expanding, what determines whether there's acceleration or deceleration, and finally there'll be a summary and an outlook. Cosmology is possibly the most ambitious science of all. I mean, if you take it seriously and say, we want to describe the whole universe has quite a lot of components. I've shown some here. And yeah, obviously that's not what we're going to do in detail. We're not going to describe in detail every single thing that is in the universe. Instead, we're going to do what all physicists do, what all astronomers do. We're going to look at simplified models. And physics, in a nutshell, is the art of finding models that are simplified enough so we can actually handle them, yet are powerful enough to actually explain things that we can observe. And that's exactly what we need to do now here on the level of cosmology. And the reason why we do not need to worry about cats or about conferences or about moons or about bugs is that we have different length scales. So here's an overview. You know the length scales. So insects are small, cats are smaller than humans. Interestingly, logarithmically speaking, cities are closer to planets than to humans, as you can see. Then we have stars, and you can see that cosmology really starts all the way over here. I mean, not even here, that's a single galaxy. So everything beyond here, that's where it starts to become interesting. So the scale not the interior structure of galaxies, but the scale of groups of galaxies, of clusters of galaxies, of everything that is larger than these structure. So that's the level of scale that we're looking at, and of course the level of detail is very coarse. For us, in the context of cosmology, in particular with the homogeneous models that we will be looking at in this lecture, galaxies are something like cosmic point particles. We do not even care about the structure of galaxies. They are just little objects that move, and we want to understand how they move and what happens if we send light from one of them to another. So that, you will admit, is much more simple than we have than the aim of explaining cats and humans and everything else in between. And that's what we're going to proceed to do now. What is the dominant interaction on large scales? You've heard this before. It's gravity. And you've also heard before why that is. Of course, electromagnetism. When you look at the usual particles that we deal with, electromagnetism is much stronger. If you look at a proton and an electron, for instance. So on short scales and in everything that determines the structure of matter and the way that different kinds of matter interact, these other interactions will dominate. So LHC, the LHC physicists will not need to worry all that much about gravity when it comes to interpreting their measurements. But since there are positive and negative charges, electrical charges, and since these attract each other and form bound systems, if we go to larger and larger scales, we will come to the point where all the objects are electrically neutral. That is the case for astrophysics on larger scales. And that is when the weak gravitational interactions that were in the background at all smaller scales and whenever electrical charges were involved, when they suddenly become important, because there's no negative gravitational charge. Gravitational influence, gravitational sources can only add up. And on the scales of cosmology or even astrophysics, gravity has added up to so much that it really dominates what is happening. And the modern description of gravity is Einstein's general theory of relativity, first published in late 1915, where gravity is linked to the distortion of space and time. And if you ask what that means, then we'll dive right into that formalism, and we'll need to look at all the definitions of curvature and what is straight and how do clocks work. And so actually what this kind of trying to find out what in the cosmological context means distortion of space and time, that is something that we want to avoid. We want to stay as close as possible to classical physics, and that, as I said, serves us surprisingly well and brings us surprisingly far. So the essence of general relativity is comparatively simple, and there's not a word of metric and censors in what I'm going to describe now. The first principle is the equivalence principle. In free fall, special relativity is valid locally. Then we have sort of the docking principle. Einstein's theory is a better theory of gravity than Newton's. It makes more precise predictions, and those are borne out to a greater extent than the Newtonian predictions, so that's why it's a better theory. But Newtonian theory was pretty good when it came to describing planetary systems, gravitation on Earth. So yes, it was a requirement from the very beginning that Einstein's theory should contain Newton's theory as a limiting case. And that is something that we know about general relativity, so that's something that we're going to use as well. Then the third input that we're going to use is that there's a bit more about what the sources of gravity are. In Newtonian gravity, you know that the sources are masses, and that's it. Since you know special relativity, you know that this can't be all, because, for instance, we've seen in special relativity that mass and energy cannot really be separated. If you go further, then you know that even energy and momentum cannot be separated. So if you transform from one system to another, these quantities will mix. Energy and momentum are somehow different sides of the same coin. So it should come as no surprise that general relativity says, yes, the sources of gravity are all these: energy, rest mass, even momentum, or what you get if you have momentum of lots of little particles running around, which would be pressure. All these are sources of gravity. All right, let's look at this in more detail. Again, these are all the first two are the interfaces of general relativity with its precursor theories. The equivalence principle gives you the link between general and special relativity, and the Newtonian limit gives you the link between relativistic gravity and Newtonian gravity. So first, the equivalence principle. That is rather simple, and that was also true in Newton's theory as well. If you are in a small cabin, you have no way of looking outside, you have no way of determining what's going on around you, and if that cabin should suddenly transition into free fall, freely falling in the gravitational field of the Earth, then pretty much all the effects of gravity that you know by experiment will vanish. If I have a sphere and if I drop it, that's an immediate effect of gravity. If I were in a free-falling cabin and would let go of the sphere, then it would just keep floating, or maybe move very slightly if I've nudged it a little bit. It will, but the usual effect of gravity, pulling my little sphere downward, would be gone. So there are no local differences between a gravity-free situation that is shown on the right there. That's an astronaut floating in a cabin in space, far away from any sources of gravity. But this unlucky person would certainly, as long as the free fall lasts, also feel only microgravity, just all the usual effects of gravity have vanished. So is gravity really gone if I'm in free fall? And that's an interesting question. And if you make the cabin large enough, you will see that even in free fall, there's something that remains of gravity. And you can see in this situation here, you can see that the elevator cabin is fairly large. I mean, this is the Earth, right? And if I now let the cabin fall, then these have moved a little bit closer together because they're not falling in parallel, they're both falling towards the center of the Earth. So even if I'm in free fall, if I have these little spheres floating in front of me, I see them floating, I don't see them falling down, we are all falling together, but I would see that they're moving inward a little bit. And that is an indication that I'm not in a gravity-free situation, that there is sort of a remnant of gravitational forces. And since these remnants are related to how gravity varies from location to location, these are called tidal forces, because as you know, the main reason for the tides are exactly these variations in the strength of gravity that is pulling both on the Earth and on the ocean. Whoops. Okay, so what do tidal forces do? And we've seen one effect. I mean, imagine that this is the mass and these are falling objects. You can see this effect, that these objects that are separated in a sideways direction, these objects come closer together. But also, if I have objects at different distances, you know that gravity is stronger the closer you come to the mass. So this object is going to feel a stronger pull, this a slightly weaker pull. So these are going to separate in this direction as well as they fall down. So in the end, there's two effects, and I've shown both of them here. So if this symbolizes a sphere of particles falling together, initially it's really a sphere, then what gravity does is it transforms this sphere into an ellipsoid. And if you want to do the calculation, you can even do the Newtonian calculation. You will find that the acceleration of the volume change is zero when these particles start their motion. So that is a description of what tidal forces do. That is true in Newtonian gravity, but that also works in general relativity. So what is if I take the same sphere of test particles, but now I'm putting a mass inside that sphere? That's the situation pictured here. There's a mass m in here. And you can very easily calculate, and in fact we're going to calculate something just like that in the end, a little bit later when we come to the dynamics of cosmology. You can easily calculate that now you have something like an acceleration now set in a ratio with the volume itself, but that is now non-zero, but is equal to this here, minus 4 pi gravitational constant, and rho in this case, for small objects, the average density within the sphere. You've probably seen something like that in a different context. It's usually written in terms of differential operators as a Poisson equation, field equation for the gravitational for the gravitational field. But what this does, it tells you something. How does a sphere of freely falling particles change? And if there is a mass on the inside, it's really not surprising that the sphere is contracting a little bit. And this again is almost true in general relativity as well. We can take the same simple test situation, look at the same setup, and find the same, except that there's now these extra terms. This is these would be pressure terms. In this case, the general case, non-isotropic pressure, 3 different directions. If it's isotropic, then you would just have 3p, the usual pressure. So this is what changes, because mass is not separate, but because we have energy, momentum, and thus pressure in there. This is really what the general relativistic correction is in this case. And if you don't know the article, there is a very nice article by Bayes and Bunn, 2005, where they really show you, calculating tensors and everything, they really show you that Einstein's field equations, the centerpiece of general relativity, can really be written in this very simple form if you go into a freely falling system, if you look at a very local, very small situation. All right, so that's actually all that we need to know. That's actually all that we need to know about general relativity, and it's not a lot. And most of it is borrowed from other theories. You can understand the volume acceleration thing from Newtonian theory. You can understand the equivalence principle, except that Einstein now says, oh, and what is true in the freely falling cabin is the special theory of relativity, the special theory of relativity. So you can understand these very simply without the formalism, and we will see that these two are very powerful tools to do what we set out to do, and that is to understand cosmology. So what is a suitable simplified model for the cosmos? This is a diagram where I've really taken standard candle data from the NAD catalog and plotted it. So that's why it's not as rich as other catalogs. But what's important is what you can see is that galaxies in the cosmos are really fairly evenly distributed. I mean, there's some noise, some areas where there's more galaxies, some where there's less galaxies. So of course there's going to be some irregularities, but on the whole, these galaxies are distributed fairly evenly. Except for this little part, that seems a little bit empty, but that's a property of the diagram. In reality, this is sort of a wedge, and of course at the thin edge of the wedge, you don't have a lot of volume, so you don't have a lot of galaxies. And here out there it begins to thin out, but that's a common effect with surveys of any kind. As you go to dimmer objects, you simply do not catch, and in this case cannot reliably estimate the distances for the dimmer objects. So if you take into account these two effects, then this is fairly convincing evidence that the universe is really, on average, homogeneous. All the galaxies are pretty much distributed evenly. If you take a very big volume, a few hundred million light years, and count the galaxies, and if you now do the same in another area of the cosmos, then you are going to get the same average answer. Okay, so that's why the simplest model that we talk about in cosmology is basically the idealized version of that. We say, well, on average, the universe is homogeneous, so in our model, we assume that it is precisely homogeneous. That's what models do, they idealize. And this has also been called the cosmological principle, By Bondi, the first instance I found is in a book from 1952. The universe presents the same aspect from every point except for local irregularities. And as you know, that continues a long trend of humans taking themselves not so seriously anymore. So we used to think that our planet was the center of everything. We used to think that we were special in the animal world before Darwin came along. So this is the cosmological version that says our cosmic neighborhood, even on scales of our galaxy and beyond, is really nothing special. On average, everything is the same. So, and since we talk about models, it's important that in the following we are going to use two different models in parallel. The one model is we're going to say, oh, there's galaxies basically floating around. That's what we're going to use if we're asking questions like, so how long will it take light from this galaxy to reach this other galaxy, and what will happen to the light on the way? But on the other hand, if we talk about dynamics in particular, we're going to go much further and we're going to say, well, the universe is really a continuum, and this continuum is described by a constant density, constant in space at least. This density, as we will see, is going to vary over time, of course. So, and if you look very closely, these are not really compatible, because in a continuum you can go to arbitrarily small scales, whereas here, if you go to smaller scales, you will find these galaxies. But they both describe various aspects or different aspects of the same universe. So we are going to be proper humans. We can hold slightly contradictory ideas in our heads at the same time. And in this case, it's really not that much of a stretch. So we're going to think about this point particle universe with point-like galaxies and the complete continuum of a universe as representing the same cosmos. Another simplification is galaxies are moving. There are galaxy clusters, and these clusters, galaxies, are basically orbiting each other. That too is something that we're going to just neglect. In the end, if we want, we can come back and see whether that was justified, whether that does anything for the predictive power of our models. Then you would see that no, it doesn't, it's okay. But this is a complication, that galaxies really attract each other and orbit around each other. That is a complication that we're going to set aside until we have formulated our overall model of the universe. Okay, so when we have a homogeneous and isotropic universe, that restricts what can happen to this universe. For instance, what cannot happen is that now all matter suddenly moves to one spot, leaving an empty area all around. So this would mean that from an initially homogeneous universe, we are now creating an inhomogeneous universe. So this kind of change would not be compatible with homogeneity and with isotropy. This cannot happen. The simplest thing that can happen that does not change homogeneity is, of course, that nothing happens. If nothing happens, then a universe that starts out as homogeneous remains homogeneous. So that is permissible. And that would mean a constant pattern. How is that pattern defined? I just look at the pairwise distances between all those galaxies. And these pairwise distances remain constant over time. That's how I know the pattern is not changing. That would be the simplest case. The problem is that as soon as we look at dynamics, of course all the galaxies, of course all the matter in the universe is attracting each other. So that means that I would have to think about something to stabilize such a universe. Einstein tried to do this in 1970, but in the end he failed. There's no way within general relativity to have a stable, static universe of this kind. Okay, if that simple version doesn't work, we'll go to the next complicated one. So what can we change if the universe is homogeneous, or if we want to preserve this pattern? Well, we can, if we want to preserve the pattern, which means preserving the ratios between the pairwise distances, then what we can still do is scale everything up or scale everything down. Now we can make more precise what that means. We have this pattern, and this is actually the same pattern, but with all the galaxies further apart. And all the distances that were defined in this cube have now been multiplied with the same factor to give us the distances here on the right-hand side. And this is the central idea of all that we're going to do in the rest of this talk. We're going to look at cosmic expansion with a universal scale factor. Universal because it applies to all the intergalactic distances of our point galaxies and because it affects them all in the same way. It's easier to see this in a two-dimensional setting, so here is a section, a small section of the universe, and we have a mere 8 galaxies, which we have numbered. The configuration is completely described by what I will call the Dij, where I is the index of one galaxy and j is the galaxy, the index of another galaxy. So for instance, here is D12, that's the distance between the galaxy number 1 and galaxy number 2. And again, in a static universe, all these Dij, all these distances between pairs of galaxies would remain constant. And what we've just talked about with them not remaining constant, but with everything changes, this is what we need to do for this. So Dij at any time t is this fraction, which is the scale factor a at that time t, divided by the scale factor a at some time t0, times the distance between I and j at time 0. This is the mathematical formula that expresses what we said, namely that all distances change in proportion to the same universal scale factor, which here we have called a of t. So if we let this go on, then you will see all the distances grow. And if you were to measure the ratios between the different distances here, you would notice that the ratios, of course, stay the same because they're all scaled in the same way. And that is our definition of cosmic expansion. And it's as simple as that. And people tend to have much more complicated ideas. They tend to think, oh, if something is expanding, it is getting larger, and then you get to these very complicated ideas. Does the universe have a boundary? Is this boundary moving outward? Is the volume of the universe becoming larger? You do not need, at this point, you do not need to worry about any of that, because this is the definition we are using. This is what cosmic expansion means for us. And the only thing we need to define this is distances between galaxies. We do not need to worry about anything else. So next we're going to look at some consequences of this kind of cosmic expansion. And the first consequence is, so now for all these distances, for instance, between the galaxy I and galaxy J, they're all function of time. But they're all functions of time in the same way, right? The only time-dependent quantity here is this scale factor. So if we now define a kind of speed in this way by just taking the derivative of Dij with respect to time, then we can calculate this, and what it turns out to be is, I mean, we just calculate this right here. This is the original time-dependent distance times this factor in front here. This factor is commonly called the Hubble parameter. It's defined like this. And this equation here is known as the Hubble relation. It links the speed at which these intergalactic distances are changing directly to the distances as they are at this moment. And that's a huge consequence. Suddenly we have a systematic relation between quantities that in most of the rest of physics are independent. Mostly if we have an object here or an object there, its velocity does not depend on how far away it is from us. It can move this way or this way, but since we have imposed this cosmic expansion condition, that is why suddenly these kinds of movements are systematic. And that, of course, is hugely important, because we're going to use it to actually find observational consequences of this particular expansion model. All right, so Everything that follows next is going to use this kind of argument. It's a local argument using symmetry. So in the simplified model, scale factor expansion, think about the continuum now, scale factor expansion is valid on all scales. So we can apply it to very small distances as well, as long as the only thing we want to calculate is how things change in a cosmological way. Galaxies in our model are in free fall. The only thing acting on them is gravity, and that is the definition of free fall. And this free fall that results in this changing pattern that is cosmic expansion is called the Hubble flow. So galaxies are in free fall, that was part of our model, and this particular change in pattern, namely this cosmic expansion with the scale factor, that is what's known as the Hubble flow. And now we go back to the two things, or to the two of the three things that we talked about with general relativity. So first of all, the equivalence principle. If I am an observer in free fall, and if I do not look too far out, do not make my cabin where I do my experiments so large, so if I'm really looking at my local physics only, I can use the rules of special relativity. That's an important thing to know. That's an important thing we know about these galaxies because they are in free fall. And the other thing, I mean, what does special relativity entail, or what does general relativity entail? If I look at a situation where the speeds are very small compared to the speed of light, all motions and all ways that something is changing and moving in space, if all these speeds are very small compared to the speed of light, then I know that I should find something like the Newtonian limit. So whatever gravitational influence remains should be described to a good approximation by Newton's theory. And what we are going to do several times now is we are going to argue, we go to small scales, we argue about some local relationship, for instance, linking the density or with a scale factor, or linking the properties of light with a scale factor. And everything that we learn about the scale factor, we can scale up, because the scale factor is the same whether I apply it locally or whether I apply it on the largest cosmological scales possible. So this is the strategy that makes these simple statements about general relativity, the equivalence principle, the Newtonian limit, so powerful, and that is that in this situation we can scale down because we know everything is true on small scales. That's the basically the homogeneous universe that we defined. Then we do calculations on these small scales, and if the relations that hold locally will hold in all cases that involves the scale factor. Now that was a rather abstract strategy. We're going to have several concrete applications now. First of all, let's look at the local universe around one of those galaxies. In the local universe, I can say, oh, the next galaxy is moving as part of the Hubble flow. In the local universe, I can use the usual terms of describing motions. So the galaxy that I see is moving away. And what does happen if a galaxy is moving away and it's emitting light towards me? What's happening is that this light gets Doppler shifted. And on small scales, again, that is a perfectly straightforward explanation of what happens. So at least on small scales, I've now derived that light of other galaxies in the Hubble flow that is coming towards me gets redshifted. And I can actually relate this, so here's the redshift, and I can relate this velocity that we derived here to the redshift. So now I have a Hubble relation that links something that I can hopefully determine. We're going to talk more about that later, and something that I can measure. So I'm well on my way of linking this model that I've introduced to observational tests. Of course, you all know how we measure these redshifts. Luckily, galaxies, just as stars do, have very fine lines, sometimes emission lines, sometimes absorption lines. So seeing how the pattern of these lines shifts means that it's comparatively straightforward to actually measure these redshifts. So that's a good link, that's a good quantity that you can actually observe. All right, that was a first very simple application of the principle that locally, in this case, I've applied what I know about classical physics. That is basically the theoretical knowledge that is necessary to understand these diagrams. So here we do have the distance, here we do have the velocity. The distance scale, of course, in this diagram from Hubble 1929 is totally wrong in a systematic way, but the fact that there is a linear relation that does hold. And the modern interpretation of these diagrams is that they represent just what we had derived, namely a Hubble relation, a systematic relation between the distance of some distant galaxy to us and the radial velocity or the redshift that we're measuring for that galaxy. And if you look at this diagram, you might say, well, isn't that rather a cloud of points? Could Hubble really be sure that this was due to an expanding universe? And Johannes Fröschle, who's also one of the co-organizers here, has actually addressed this in his Staatsexamensarbeit. He did a Bayesian analysis, and it turns out that yes, even with the predecessors of Hubble, and certainly with Hubble, you can be fairly certain that what you're seeing is not a static universe with a chance alignment of galaxies, but really a linearly expanding universe. All right, so measurements, of course, have become much more precise since Hubble's time. I'm just picking out the Hubble relation as observed by the Hubble Key Project. So the reason that the Hubble Space Telescope really deserves its name is that it was used for this particular project, which is determining all these distances now going much farther away for galaxies or supernovae much more precisely. And you can see that, yes, this is a linear relation. So, and there's no good alternative explanation that I know of why this linear relation should exist than what we've just derived very simply, and that is the Hubble relation. So this is a very simple derivation that, of course, is suitable for students. So we haven't done anything serious yet. But this is already something that links very directly to observational data, and that shows strong support for this model of an expanding universe that we're looking at. Let's do something a little more complex. Let's again go to a very small area. Let's again look at some local space around one observing galaxy. And now let's take another law that's valid in classical physics, and that is energy conservation. Here in the thermodynamic form, the change in energy, interior energy, is the heat that is transferred to the system diminished by the work related to the system. So P is the pressure, V is the volume, U is the whole internal energy of the system, and Q is the heat. In our case, everything is homogeneous, so there's really no outside, no inside, so heat should not even flow from one point to another, and so there's really no heat term that we need to introduce here. There is no way that heat is coming somehow from outside into the universe or into this region that we're looking at. So formula becomes even simpler because we can just cross out this here. So the mass, let's link this to quantities we've already looked at. So the mass density corresponds to the total energy here. So rho c squared v, v just to make the density into an absolute quantity, and rho c squared, that's just E equals mc squared, linking the mass and the energy. So there we have the U term basically linked back to a term that's very interesting for us, namely to the density rho of the universe. So we can rewrite this as follows. We've just applied the usual Leibniz rule to this bit here, And now we have the change in density is related to the relative change in volume in this way. But we know how the volume changes. Because again, look in this very simple local situation, look at a cube, side length L or whatever. If I'm looking at a cube that is expanding with the universe, so I'm looking at basically the same assembly of particles and I'm following them through the expansion, then all the sides of the cube are going to change in the same way, namely proportional to the scale factor A. So since the cube is by definition side length cube, the volume itself is going to change in this way. So I can actually transform this differential, this expression here, into this right-hand side linking the change in the scale factor and the scale factor. So this gives us this expression here. Now we have linked the change in density with the change in scale factor. I can also write this, as d rho dt, and on the other hand dA dt. So I can take the cosmic time derivative and rewrite it like this. This would be how densities change over time. Now it's immediately obvious that I need additional information if I want to really calculate what that means. And the additional information that I need is usually called the equation of state. So in this simple incarnation, it just links the pressure of some kind of matter with the matter density. And we'll just use very simple examples. If I have galaxies that are just drifting along, they're not moving in any way except in the Hubble flow. They're not interacting, so there's no pressure at all. It's just a density, but no pressure. So P equals 0 is what I use for, I call this matter. We could also call it galaxy dust. For electromagnetic radiation, this is different, right? So I have P equal rho c squared over 3. So basically rho over 3. That is something that Maxwell already derived and is something that we now take on board from our physics colleagues in order to put into our model. So if we're dealing with radiation, think for instance of a cosmos filled with thermal radiation. If we are dealing with that, then we have this equation of state. And then there comes a weird thing from the particle physicists, and general relativists actually discovered something similar. It is something that has this equation of state here, and that's known as a scalar field. In the context of cosmology, it's known as dark energy. I'm not passing any judgment at this point. I'm just saying it is a possible equation of state. We should see what consequences it has. So, and as it turns out, this actually covers most of the cases that are interesting for cosmology. And as you can see, these equations are all very similar. So I can actually describe them in a unified way, introducing this parameter W. And here I've given you the values of W. All right, so now it's just a matter of calculating. I'm putting the slides up so you can do this yourself. It doesn't make sense that we do it, but it's straightforward derivatives, it's straightforward substitution, and we have one differential equation, and you can see this is going to integrate up to become a logarithm. This is going to integrate up to become a logarithm. So this is the solution. So for these three simple kinds of matter, I can readily tell you how scale factor expansion is going to change their densities. For dark energy, this 1 plus W is 0, so that density does not change at all. And that is why in some way people have, nobody really knows what dark energy is, but if you look at the speculative interpretations, people will say, well, maybe it's sort of a quantity really associated with space, because if you have twice the space, then you obviously have twice the dark energy, because its energy density remains constant, it does not thin out. We don't have to go there. The only thing that interests us in this context is that it has this particular scaling behavior for the density. Galaxy dust, if you plug that in there, the 0, then you see the density is rho at the time t is equal to rho at the time 0, and then times this scale factor. And again, that is unsurprising because galaxies don't just get lost, not even in an expanding universe. No galaxies will spontaneously come into existence or suddenly pop away. So if I have the same number of galaxies representing the same total mass, and if I just put them into a larger and larger volume, and we've seen that volume, of course, scales with the third power of the scale factor because you're looking at a cube, then, of course, the density in this situation must go down in this way. So we have only rederived something that we have already known, which is good. It's a consistency check, right? I mean, in particular, if you're doing things in a heuristic way, like here, where you're saying, oh, this is very small, I'm going to use this approximation, it's always good to do consistency checks and to see that things really work out the way that you expect. So let's go on. More interesting is electromagnetic radiation. And we know that electromagnetic radiation is something like a photon gas. So we have photons, and these photons coast along at the speed of light, and altogether in a thermal situation we know that they have a certain Planck spectrum, so we know something more about them. But even if we just knew that there's photons, and these photons have a certain energy that is related, as we know, to their wavelength or to their frequency, then we could do the following argument. Here are some little colorful photons just coasting along. Photons too do not get lost, at least not in this sort of semi-classical picture that we're looking at here. So these photons really coast along, we can always follow them, and that means that the first thing we would expect is the photon energy / mass density should certainly have a factor that is proportional to minus the third power, because that just means we have the same number of photons, but we are now distributing those photons in a larger space. But that is not all that happens, because we have an additional factor here. The density changes more quickly. There's an additional power -1 here. And there is not so much that this can actually be. So this actually tells us about something that is important for photons. What is the energy of a photon? We know it's E equals h, Planck's constant, times the photon's frequency. Or if we want to use the wavelength, it's hc over lambda, the wavelength. So if the total density derived from the energy density of the photons changes in this way, it must be that the wavelength of each single photon is getting longer in an expanding universe in this way. That is the only property of the photon that we still have left to change. And this is a more powerful application of our principle of looking at things locally, because we looked at an energy conservation law. We looked at what this meant in the context of matter with certain kinds of pressure, and then we found that in an expanding universe, the only way that things are consistent is if light is redshifted. Now again, this is not completely new, because we have already seen this Doppler interpretation at very close range, but now we know something about how this redshift is directly related to the scale factor. Wavelengths, just as distances between galaxies in the Hubble flow, grow in proportion to the scale factor, and that is an important piece of information. It is particularly important because while we have just argued locally up to now, we can now splice together these different local pieces of knowledge that the wavelength is expanding in proportion to the scale factor. So assume that a photon is moving in this direction. This is the time that it was emitted. This is the time that it was received somewhere else. Then we can split this into various small pieces. And if we make the pieces small enough, then in each region that we're looking at here, we can make our local argument. And our local argument says the wavelength changes in proportion to this ratio of scale factors. So now we can say how it changes from here to here. In this way, from here to here, this additional factor this additional factor, this additional factor. And I mean, I've just written out 9 of these different times, so plus emission and reception time. We can make this arbitrarily small, and then these regions where we apply our local knowledge will become arbitrarily small as well. But as you see, this is very nice, because this here just goes away. These two in the numerator, denominator, these all go away. And the only thing that that is left is that the received wavelength of this photon with expressed through the emitted wavelength is just related to the scale factor at the time of reception and the scale factor at the time of emission. And this is now a result that is true globally. It is true for any emission time, for any reception time, because we have used our local knowledge to just piecewise splice everything together. And this result is no approximation. This is really something that holds globally. So that is basically the generalization of this cosmological redshift that we had derived as a Doppler shift, but now we know a precise formulation in terms of the scale factor. So that's a hugely important piece of information right there. At this point, though, we've been a little fast, right? I mean, we've talked locally about times. We've introduced A of t with t a time coordinate, but we haven't really looked at the details of what this time coordinate means. And if you look closely, then we do have a few surprises there. So v equals h times d means that if you have the distance large enough, then you have recession speeds that are faster than light. How can that work when we are working within the framework of relativity? So that's at least puzzling at first glance. The second thing is, and I'm wondering that nobody has complained, we've just derived that single photons in a way are losing energy. But we had derived everything from at least some version of local energy conservation. So how does that work? And the solution in both cases is the same. This t is weird. We have used t locally around each galaxy as an ordinary time coordinate for determining Newtonian orbits, to determining special relativistic motions. And locally, everything was okay. But now we're doing something different. We're using t, and we're extending this time coordinate from one galaxy to another galaxy. So what does t mean there? T must also be at that galaxy the local time as measured by clocks on that galaxy. Why does that have to be the case? Because otherwise, these two galaxies would have a different function describing A of t, the scale factor. Homogeneity means that if I locally compare what happens with the scale factor with, for instance, a clock that is running on my galaxy, I must get the same result at each galaxy. So somehow implicitly we have introduced a time coordinate that uses local galaxy time everywhere. But we know from special relativity that this is not the usual time coordinate of special relativity, because we know that if two objects are moving relative to each other, then there's going to be relativistic time dilation. So the global time coordinate that one of them defines is not going to be the same as what the moving clock of the other galaxy shows. So that is the solution in this case. Superluminal galaxy motion really is a coordinate effect in that particular sense. There exists a more proper generalization of what relative speeds are in general relativity. It's called parallel transport, and there's some nice articles on it that I'm going to put into the written version of this talk. So, but the fact that I have these weird superluminal velocities really is a direct consequence of me choosing this unusual but highly homogeneous and suitable time coordinate. And the same with the energy loss. The galaxies, the emitting galaxy and the receiving galaxy are in relative motion. The distances are changing. If I look at close distance, then I can even use my ordinary classic understanding of motion. So of course, the wavelength measured by the one galaxy is going to be something different than the wavelength measured by the other. That is what the Doppler effect is all about. And nobody would think to complain because, oh, has the photon lost energy on the way? No, it hasn't. It's a matter of looking at the same photon from two different systems that are in motion relative to each other. And this solution works here as well. Again, if you use the proper relativistic generalization of what it means for objects to be in relative motion, then you can even go as far and see that the special relativistic Doppler formula holds throughout the whole of general relativistic cosmology. So again, I'm not going to go into details here because that is certainly one or two other talks right there. But the only thing we should remember is that t, as viewed as a global coordinate, is unusual. And we should not think that we can deduce anything from our pre-existing knowledge without calculating explicitly when it comes to this t. When we are locally on a free-falling galaxy, everything is okay. There, t is really the local time as measured by a free-falling observer. It is really the local time that we use when we do Newtonian mechanics or special relativity. All right, onwards with the consequences. Light propagation. We can do the same thing. We have a galaxy in free fall. We have a very small area around the galaxy where we say, yes, we can describe light propagation in the way that special relativity describes light propagation. We need to take a little care about how we measure distances because, as you can see, when we compare these distances here, we will need to take into account that these distances between the moving galaxies have changed over time. So if we take the distance delta r, which is defined for all these galaxies at the time the light signal is received, then we will need to correct this distance using the scale factor to describe these little partial distances. Now that's a bit of a problem if we want to do the calculations, because right there as it stands we have a time, a total time on the left-hand side, and we have many different times that we do not know before we have done the calculation on the right-hand side. So what's actually better to do is to look at these pieces separately. Here I've written them in an infinitesimal form, and then we put everything that contains the cosmic time t on the left-hand side, everything else on the right-hand side, and then we integrate up, and that is basically our formula for calculating travel times, light travel times in our expanding universe. And again, we have not used the metric, we have not used anything except our local knowledge, and being very, very careful how we extend this local knowledge to larger scales. One result that you can derive from there, you can rederive the cosmic redshift and its relation to the scale factor. You can also see that the same applies to the distances between two light particles that are traveling behind each other. The distance between these particles is going to become larger with cosmic time as well, in proportion to the scale factor. So in addition to cosmic redshift, there's really something like cosmic time dilation. Things that are emitted in very short order, very quickly, one after the other, from a disk galaxy are going to arrive at me at the receiving end with a much larger distance and more slowly spaced. All right, next question is, how do objects get dimmer? And this is the first point where I have to go beyond the simple assumptions that I've made so far. I have to introduce an additional assumption, namely that geometry in my space as defined by a snapshot of everything at constant cosmic time t, I'm assuming that for this space, geometry is flat. That is a big assumption. General relativity in general admits more general space geometries. As it turns out, for our universe, this particular universe that we are in, it is a correct assumption. Our space is flat. So, but this is, and I just hasten to point out, this is where I'm getting, where I need an additional assumption. But once I have that assumption, I can really calculate how does the light of distant objects get dimmer with distance. So initial energy output, luminosity L, something along the lines of energy per second. photons spread out evenly over a spherical surface, what is the size of that spherical surface now? If the usual flat geometry applies, it's 4 pi r squared, and the radius is just the distance at this point in time, at the present time, of the emitting galaxy and my receiving galaxy at this present time. That is what determines how photons spread out over the sphere. But then there are additional effects. What I really want to measure with the detector is how much energy reaches the detector per unit detector area, per unit time. But as we have seen, the photons are redshifted. So if I'm comparing energy emitted and energy that reaches me, every single photon is redshifted, so that diminishes the energy right there. And that's not all, because also we've seen that there's the cosmological time dilation. So if a steady stream of photons, a certain number of photons in a certain unit time, departs from this source, then these photons will be spaced farther apart and reach me at a slower rate when they reach me. That is just cosmic time dilation. So that gives us an additional factor of 1 over 1 plus c, or this scale factor, that I need to include in my formula. 1 for the rate of photons reaching me, and 1 for the energy of each individual photon, which is diminished by redshift. So if I put everything together, then my expression for the flux density I is the following. So here is the luminosity up there. Down here is the distance square. That is, in fact, so far we're doing nothing different from the non-cosmological case. That's the usual inverse square law. The only thing I need to note is that this distance is the distance evaluated at the time tr at the time that the light reaches my detector. And I have this additional factor, 1 plus z square. And that is new. That is something that comes into play directly through the cosmological redshift and the cosmological time dilation. So if you look at this formula, it's really not that different from the usual inverse square law, except that I have this 1 plus z square factor. So what is sometimes done is that I define a new concept of distance called the luminosity distance. And the luminosity distance is simply the ordinary distance evaluated at the reception time here times 1 plus z. And as you can see, if I substitute that into my inverse square law formula with this luminosity distance, the formula looks exactly as it would look in classical physics. So if I look at this formula, I can measure everything but the distance, and that means that I can solve for the distance. The flux density is what I measure, what I observe with the telescope here on Earth, just photometry, how bright that object is. The 1 plus z, the redshift z, I can determine from looking at the spectral lines, for instance, of a distant galaxy, by seeing how these spectral lines are shifted. I have a direct measure of z. So the only thing that I still need is this L. If I know the L, then I'm home free. I can then determine the distance. And recall now the definition of a standard candle in astronomy. A standard candle is an object where I can use certain measurements to determine L. So 2 very prominent examples. The first are Cepheid variable stars. These stars get brighter and less bright periodically. And the period of this brightness oscillation is directly related to the luminosity of these variable stars. So the period I can measure. From that, I can use the period luminosity relation first found by Henrietta Swan-Leavitt to determine the luminosity. And once I have the luminosity, I can deduce the distance from this formula. The second example we've already seen in the very beginning. It's the supernovae of type 1a, stellar explosions of a certain kind. These are almost all equally bright, so L is fairly constant in that case, and there is a refined formula where you can see how after this very bright peak brightness, if you determine the time scale on which the brightness of the supernova dims, then you can deduce the peak brightness and thus the luminosity even more precisely, and that is a very precise way of determining luminosity and hence of determining distances to these distant supernovae. So this is how I use this formula. With standard candles and measurable, directly measurable quantities, I can deduce the distance. So this is the crucial cosmological version of basically how objects dim as they go farther away, and that is a crucial part of how we actually reconstruct how far objects are away. Okay, we just have one last question left, and that is, we've always talked about A of t, and we've derived certain consequences that this expansion proportional to A of t has, but we haven't said anything about what is A of t. How is it related to the matter that we have in the universe? But again, this is very simple, and again, we do the same that we've always done. This is sometimes called a Newtonian analog, but it's really not an analog. But because what we are doing is same thing we've always been doing here, same strategy. We look at very small scales. At these very small scales, freely falling galaxy, equivalence principle, everything is as it would be in special relativity. If we go to small velocities, and as we've seen that Hubble relation velocities grow with distance, then going to a smaller region automatically gives us smaller velocities in the Hubble flow. So if we put all this together, then as long as we go to very minute scales, then we can use the Newtonian calculation. And whatever we find out locally about A of t is going to be valid generally, simply because, again, the scale factor is the same throughout the universe. It's universal. So now that we go to this very small region, here is our origin. This is where we are. Now within this region we have a test galaxy. So how does the distance here called R of t, which again depends on the scale factor, how does that change over time? And we've seen that it's perfectly valid to make a Newtonian calculation, and Newtonian gravity makes these things very simple. We are in a homogeneous isotropic universe. That means that we can see all the exterior matter as composed of shells of matter surrounding us. But Newton has a very general result for the influence of a spherical shell of matter that is outside of where we are. And the Newtonian result is that this shell is not going to do anything. Zilch, zero, nothing. So we can neglect all the matter that is outside, and the only thing we need is the amount of matter, cosmic matter, that is inside. And Newton has something simple to say about this again. He says that the gravitational field of a sphere or any spherically symmetric body, as viewed from the outside, is the same as if the mass of the sphere were concentrated in a point particle in the center of the sphere. So again, very simple, and we can just write this down using the ordinary law of gravity. So this is the Newtonian formula. Now is an additional point where we insert extra knowledge from general relativity. One of the three simple statements about general relativity that I've told you in the beginning was that mass is not the only source of gravity. So here we insert the additional term. The mass now contains all the energy density as well, and we have this additional pressure term. That is the first change that we make. That's the only modification. Everything else is really Newtonian. The volume is just given like this in the usual way, and we insert the fact that the change in distance, our change in distance to that particular galaxy, is governed by the scale factor. So R of t is proportional to A of t. And if you put all this in, then you're going to get this equation for the second time derivative of the scale factor out. It's called the second Freedman equation, or the second order Freedman equation, first found by Alexander Freedman in the early 20th century. This is, if you will, our first equation for how the scale factor changes over time. And as an aside, you know that's always how it works in physics, right? I mean, dynamics is always second derivatives. It's always accelerations. So we should not be surprised that this equation that we have for the scale factor is second order, two time derivatives with respect to cosmic time, and a source term, and a source term on the other side. But recall that we had another equation, the one that we derived from energy conservation locally, the one that gave us the information of how densities change over time. If you combine this with the second order Freedman equation, then you can integrate. It has a dot dot, a dot, rho dot in just the right proportion that you can integrate on both sides without assuming anything special. This, again, in physics would mean that you go from a force equation, which is second order, to something like an energy equation, which is first order. So this is really analogous to what we're used to. So this is the new equation. We've picked up an integration constant, as one does. And as you can see, this one depends on A in a way that if we rescale A by a constant factor, we can always get this big K to be 0, plus 1, or minus 1. And a constant factor doesn't hurt us anything. In the context of general relativity, and that is something that I'm not deriving here in a simplified way, K is really linked to geometry, right? It's a spherical space or a hyperbolical space or a flat space. So, but again, that's just an aside, nothing that I have derived here. All right, and now what comes now is a bit tedious, and I apologize for that. But it's just bookkeeping. We had 3 different kinds of matter. Here they are. We have 3 different kinds of scaling behavior for these densities. We make an assumption, and that is that in order to get the total dynamics of the universe, we just add up the densities for the various forms of matter. Simple. Doesn't have to be true. If there's heavy interaction, then there could be a difference. But in our case, galaxies, radiation, dark energy, it seems to work out. So our new rho is the matter part, galaxies, the radiation part, and the dark energy part. And then there's a considerable simplification, because with all the quantities that we have, and there's not so many we have, so we have the Hubble constant, we have this G, and if we combine it in that way, it just has the physical dimension of a density. So what we are doing is we just rewrite everything so we get as dimensionless as we can. So the matter density is the matter density at present time, rescaled in the way that we derived. This is how it depends on time. And this present time value is split into a multiple or fraction of the critical density. And we do this for everything. We first use the explicit knowledge about how it scales with a scale factor. That relates the value at any time to the present time value. And the present time value we split into this dimensional big omega and the critical density, which is basically our unit density for this particular universe. And then there's this weird case c squared term. This can also be written as a dimensionless omega, and this is the definition. And now things become dimensionless. Introduce this additional factor just for convenience. This is just the relation between the scale factors, which is equal to 1 over 1 plus z. And recall that this is the definition of the Hubble parameter. And then we really get a very simple equation of this type. Everything that depends on x, we bring to the right-hand side. Everything that depends on, on time, we bring to the left-hand side. So there we are. This we can integrate. This is so simple in physical terms that we can get a mathematician to do it. It has none of these disturbing terms with physical quantities and so on. It's just something that we can integrate, and if we can't integrate it explicitly, we do it numerically on a computer. So let's just see what this is. On the right-hand side, we will have some complex expression that contains x. So x can be rewritten as a. The left-hand side is trivial, right? Integral of dt is just t at the end minus t at the beginning. So what we get is an implicit function of a in terms of t. We have to solve that for getting the explicit a as a function of t, and then we are done. Then we have described the behavior of this particular universe with this particular content of matter, of radiation, of dark energy, and we can see how the scale factor changes over time. A brief aside, building the bridge to some of the next talks. So recall that we have these different scaling behaviors. And that means that in an expanding universe where A becomes larger, these different kinds of matter tend to be important in different periods. And I've drawn this as an example logarithmically. So this is matter becoming more dense as the scale factor becomes smaller. This is radiation becoming more dense, but since it's a fourth power, not a third power, it really overtakes things here. This is dark energy remaining stubbornly constant. So that means quite generally, in a universe that is going through all the length scales with its scale factor, quite generally, in the early time, radiation will become dominant simply because of its scaling behavior. In the middle, matter is going to play some role. In the long term, dark energy is going to become more important than anything. So that means even without solving the equation, I can draw you a picture of how the scale factor is going to change. So the only thing that I need to do is I need to look at these three different phases of domination. For instance, radiation dominated. I just keep this term here, neglect all the other terms, and the resulting approximate expression is readily integrated. And I find that in this radiation-dominated case, the scale factor A is proportional to the square root of T. This is interesting in the early universe. For a matter-dominated universe, I just keep this term here. I neglect all the other terms. And again, the result is very easily integrated. And I find that the scale factor is proportional to T to the 2/3. Finally, in the dark matter-dominated case, I just keep this term here, and again, easily integrated, and I get this exponential form for the scale factor. And as you might know, this is important, for instance, for this inflationary phase that is postulated for the very, very early universe. In the inflationary phase, inflation is just this kind of exponential expansion. And that means I can tell you, even without doing the calculation, how the scale factor is going to look. In the beginning, radiation is always dominant, so it's going to look like a square root. And in the end, it's going to be exponential because dark energy dominates. So I basically can show you this. This is the more precise curve for our universe with the actual values that you get from observation. So here's the square root part that I talked about. Here's the exponential part. So and it's readily understood by simply understanding that different kinds of matter are important in different kinds of eras in the universe. All right, so now at this point, I'm not going to go through the whole process because obviously that involves taking the data, and in fact that's what's behind the exercise that you've been doing yesterday. So but at this point, and without using the metric or any complex concept, we have all the ingredients to understand this diagram, which is basically standard candles, the brightness of standard candles, the distance modulus in terms of redshift. We know how distances are related to light travel time. We have seen how brightness dims, and because all this contains here the A of t, we have seen how the scale factor depends on the matter content of the universe. So this is behind these particular observations. You take various universes, you use the simple equation that we found, the dimensionless one, to really calculate the scale factor evolution for that particular type of universe. You draw the conclusion of what that means for standard candles as a certain distance using the derivations that we have made for the luminosity distance and for, in general, for how dim objects become. So we have all these ingredients, and we have derived all these ingredients using no more than these very powerful local Newtonian, local special relativistic arguments and proper cautions about how to extend them. So this, I believe, is a very powerful statement because it really shows that, I mean, lots of what we have used is due to the symmetry, right? Every time that we've used the scale factor as a general quantity and then done our calculations locally, we've made use of the fact that the universe is isotropic and the scale factor is the same on all scales. It's universal. So that was a huge help. Otherwise, we couldn't have done it. So summary and outlook. The equivalence principle and the Newtonian limit are very, very powerful. And sometimes in some place in the literature, you feel like people are even ashamed of using this Newtonian machinery. They say, oh, and we have this Newtonian model, and we know it's not relativistic, but you can see that it works quite well. And I think people need to be much more positive about this. By going into these limits, by making use of the equivalence principle, and of this very simple form of the Einstein equations that we've seen with the tidal forces and with how volumes are contracted and the volume acceleration and so on. By using this, you can show that no, it's not just a pedagogical model, it can be made fairly exact. Paired with the symmetry, this determines most of Freedman, Lemaitre, Robertson, Walker, so most of the most current expanding universe. The only additional input in this specific derivation were the source terms. I did give you a hand-waving argument about those. That can probably be made more precise. And space geometry. And I believe, I haven't done it, haven't had the time, somewhere in the future, sometime in the future, perhaps. I believe that even there you can use the local arguments and following light along these little pieces of trajectory to derive space geometry quantities. So I believe that this is actually in there, but for my presentation of today, it was certainly an additional assumption. The outlook, or what I didn't have time for, first thing I just said, deriving the spatial geometry via the propagation of light. The discussion of the nature of cosmic expansion, that is something that has that we've discussed on quite a number of occasions. Is cosmic expansion something that drives things apart, or is it a kind of motion? I think in line with several other articles that have dealt with this, you can see from the local picture that at least locally, of course, you can validly describe it as motion. You can describe bound objects in this context. You can derive the tethered galaxy problem of basically when does an object join the Hubble flow. You can determine this. And there's also a connection between the models I've talked about here to those models that make it more explicit, at least in certain special cases, of how the artificial distance defined by your cosmic space coordinate and by slices of constant cosmic time, the recession velocities, the superluminal recession velocities are related to a proper special relativistic description. Of course, the best model for that is the Milne model. You can also simplify that by just taking certain very few systems in special relativity that move apart, and you can construct a toy cosmology. So, and that directly extends, if you will, the power of this special relativistic special case that you get if you look very closely at the locality around a galaxy. So that's it. So we've really gone through much of cosmology. If you look into the ordinary textbooks, they're going to derive it from the metric. They're going to need certain information about geodesics and so on. I hope to have convinced you that there is a proper and fairly rigorous way of doing the same by using the power of the equivalence principle and of the Newtonian limit, and of course of being very careful when you stitch these various local systems together. We've seen that we get this weird global cosmic time coordinate whether we want it or not, simply because we need to reflect this homogeneity of the cosmos. All right, so thank you for your attention, and we have certainly time for some questions.